Let us start our discussion of yield criteria for rocks with yield criteria insensitive to mean effective stress. These are not going to be applicable to rocks, but are a good introduction in order to understand more complex yield criteria. All right, so imagine that we have a bar and we pull that bar with a force F so that we create a stress along the bar. This is a test that it is usually done for testing the tensile strength and the yield stress of steel. So if let's imagine that this is a bar of steel, we can pull with the stress sigma, and the maximum stress that the bar can take is going to be called the yield stress. In this simplification, we're assuming that this yield stress after the yield point takes a constant value. This is something which is called perfect plasticity. And in perfect plasticity, the yield stress doesn't change after you go through the yield point. So in general, for a given material, the yield criterion is going to be a function that helps us decide when the state of stress reached that maximum value. And this is going to be a function of the state of stress. And this function, we're going to make it equal to, in this case, a constant k. And this is what we call this function, a yield criterion. And some other times also we can call it a failure criterion. Usually they are used as synonyms, although sometimes there might be small differences that we're going to talk about later on. Okay, so what is a state of stress composed of? In order to fully define the state of stress, we need to know the principal stresses, and not only that, we also need to know what is the direction of those stresses. And particularly, we need to know the direction of the principal stresses with respect to the geometry of the material. For example, I could have a material that has some small cracks in this direction, and the tensile strength or the yield stress is not going to be the same if I pull it, let's say, in direction X, or well, let me change since we're using Y already for yield, it's not the same if I pull it in direction 1 or if I were to pull this in direction 2. Because if I'm pulling in direction 1, very likely I'm going to take advantage of those small fractures, and that's going to give me a lower tensile strength or yield stress in direction 1 than in direction 2. So the direction of the principal stresses with respect to the geometry of the material are very important. However, we can simplify this for isotropic materials and just write the yield criterion as a function of the principal stresses. But it is very important that you know that when you go from here to there, implicitly you assume isotropy, which is that the yield stress is going to be the same in all directions. So let me find a smarter way actually to label this: sigma y1 and sigma y2. Okay, so now in this case, the yield stress is going to be the same in all directions. Okay, you could, for example, write this yield stress with this equation. We have seen that the stress tensor can be also written in terms of the invariants. And still considering isotropy, I could write the same yield criterion as a function of the invariance of the stress tensor I1, I2, and I3, and that's going to be equal to a constant, which is not going to be exactly the one I had before, but it is going to be related to that. So in summary, the yield criterion is going to be a function of the state of stress. And for isotropic material, it's just going to be a function of the principal stresses or the invariants. Okay, let's see some examples of these yield criteria. The first one that we're going to see is the one which is called the Tresca yield criterion. In the Tresca yield criterion, what we do is we fix the maximum value for the difference between the maximum and the least principal stress. For example, let's draw some more circles here. Let me make this a little bit longer. Okay, we have effective normal stress, we have shear stress in here. We perform a test of pulling like this one and we get up to the yield stress. Now we're going to take this to 3 dimensions, okay? But first let's go into 2 dimensions. The stress perpendicular to the force F is 0. In this case, I don't have any stresses around. So the least principal stress is going to be 0, and the maximum principal stress that the material can take is going to be sigma y. Let's say it's over here. The more circle for that, then is going to be something like this. And what the Tresca criterion is going to say is that the difference between the maximum and the least principal stress has to be equal or smaller than the yield stress. Where I hope that you notice from here now that, let me do it with another color, that in this case, this is our sigma 1 and this is our sigma 3. But now I am extending with the Tresca criterion this for any state of stress and also to 3 dimensions. So eventually what this equation means is that I'm going to have a limit for the size of the Mohr circle, and it cannot pass this line, where this line is going to be located at a distance of sigma y divided by 2 from the x-axis. Why sigma y divided by 2? Because it is the radius of this circle. And I could have, for example, another state of stress, for example, this one over here. And as long as the maximum principal stress, in this case, sigma 1 minus sigma 3, which is going to be, in this case, this one. Now, this sigma 1 and sigma 3 apply for the green circle. Then the material is not going to fail. And actually, this line, the yield line, is limiting the possible state of stresses. My Mohr circles cannot ever go beyond that line. Why? Because that's a yield stress, and stress cannot go over this line. Okay, let me change the color of this just to make it equal to the one I have on the right. Okay, so how do we extend now this Tresca criterion for 3 dimensions? All right, what we're going to do is we're going to write the same equations, but slightly different. And we're going to write these equations with still principal stresses, but these sigma 1 Roman, sigma 2 Roman, and sigma 3 Roman are not going to be ordered in a particular order of which one is the larger and which one is the smaller. Here, that's why I'm taking the absolute values. The difference of any principal stresses has to be, the absolute value of that has to be equal or less than the yield stress. And with these equations, what I can do is I can plot what is called a plot or a space of principal stresses. Okay, just let me add here this warning that these are not ordered in any particular order, and that's why I have the absolute values. Okay, so let's see what is going to be the result of that. When I have these equations, then I can plot those in the principal stress space. And let me start by, I think I'm going to have enough space so we can do everything just in one page. And let's start with that. Let's say that I have in a space of principal stresses with sigma 1 Roman in the x-axis, sigma 2 Roman in the y-axis, and I fix my third stress, sigma 3, to be equal to 0. Basically, in this case, what I'm doing is I'm just exploring what are the possible values of sigma 1 and sigma 2 Roman given the condition of sigma 3 Roman equal to 0. Okay, so if sigma 3 is equal to 0, and for example sigma 2 is equal to 0, and I start increasing sigma 1, this is going to be the pooling experiment in one dimension that I had before. And the maximum value for that is going to be sigma y, right? Because the other two are 0, the maximum stress I can have in the other direction is just going to be sigma y. I could do the same experiment, sigma 3 equal to 0, sigma 1 equal to 0, so now I am here, and I start increasing sigma 2 Roman, and the maximum value is going to be equal to sigma y2. So this is going to be another limit. In this case, we are also assuming that this is an isotropic material and has the same yield stress in compression as in tension. So if I were to be in compression, I could be right on the opposite value. That would be the maximum stress with all the others, one more try, equal to 0. And if I were to just to go in this direction, then this is going to be also the minimum value for sigma y. So this is sigma y, this is negative sigma y, and this is negative sigma y. Don't worry much about the signs yet. We're going to talk about that later on. Okay, let's extend now this a little bit more. Let's say that I have a sigma 3 equal to 0, and I have a sigma 2 which is not equal to 0. It's somewhere around here, but it is not negative. So in that sense, the maximum difference is going to be between sigma 3 and sigma 1. And sigma 2 is not going to play any role because it is between 0 and sigma y. So what that means is that here I could have this stress sigma 1 to go all the way to sigma y as long as sigma 2 is positive. And it's the same with sigma 1. If it's different than 0, but it is less than sigma y, as long as it is positive, I could go up to the value of sigma y. And I could also repeat that logic for going in the opposite sense of the stress. All right, but what happens, for example, if I have my sigma 3 equal to 0, and now let's say that my sigma 2 is going to, let's say my sigma 1 is going to be negative 0.5 sigma y. And now I am uh, in compression in one direction with the negative sign in this case. And the question is, what will be the maximum value of sigma 2? Well, consider sigma 3 is equal to 0, right? So the maximum difference is going to be between sigma 1 and sigma 2. And because sigma 1 is already negative, in order to guarantee that difference here, the maximum possible value of sigma 2 is going to be negative 0.5 sigma y plus 1 sigma y, which is going to be 0.5 sigma y. So it's going to be a point over here. And the same logic again is going to apply for the other side when I have a mixed state of stress with compression and tension. And at the end, what this is going to end up in, it's a limiting surface that looks like the polygon that I am drawing right now. What I have done now in this case is to extend the failure or the yield criterion to 3 dimensions, but remember with one of those stresses to be equal to 0. So what would this look now in 3 dimensions? And it's actually easier to take a look at this in 3 dimensions than in 2 dimensions. And in this case, let's make the drawing over here. Let's say I have a principal stress space. Is a right-handed space, and I have, in this case, sigma 1, sigma 2, and sigma 3 principal stresses, but not ordered in a particular direction. All right, here what I'm going to do is I'm going to define what is known as the hydrostatic axis, which is going to be the axis for which all the stresses, principal stresses, are the same. And along this axis, which is a line in 3 dimensions, sigma 1 is equal to sigma 2 and equal to sigma 3. And again, this is called the isotropic or the hydrostatic axis. And using the equations of Tresca, I can find that the limiting surface or yield surface with this criterion in 3 dimensions is going to look something like what I'm going to draw right now. It's this is a tough drawing, so I hope I can make it in the first try. Okay, let me try again these 2 last strokes. Okay, so this hexagon that you see over here in 3 dimensions translate to something similar to this, and the yield surface is going to be parallel to the hydrostatic axis, and it's going to look like a prismatic hexagon in 3 dimensions. Okay, so I hope that you can see more or less what this yield surface is. And what it means is that your state of stress can be in any location inside that surface, and it's not going to be at yield. But as soon as you reach and touch the surface of this hexagon, then your state of stress is going to be at yield. And if you look a little bit closer, and we're going to do this in a bit as well for the next stress criterion, is that you could think always that your state of stress, let's say somewhere over here, it is composed by two vectors. A vector that goes from the origin through the isotropic axis into a plane which is perpendicular to the isotropic axis, let's say at the point over here, and eventually what is limiting your state of stress is the distance from the hydrostatic axis to the yield surface. It's not really how long you go into the hydrostatic axis. You can go, according to this criterion, infinitely in this direction, infinitely in the other direction, and that doesn't matter as long as you stay within the bounds of the hexagon. And here what it really matters is that distance. All right, so this is what is called the Tresca criterion, and it is not very popular in computational mechanics because of these sharp edges. And this is actually a discontinuous function with two derivatives coming from each side. And well, it's not actually discontinuous, but it's not continuously derivable. And having two derivatives from each side, it makes it not very easy to deal with in computational mechanics. So rather than that, what we could look for is another type of criterion similar to this, but with smooth edges. And that's what the von Mises criterion does. And let me scroll down. Here, the von Mises criterion is going to try to address that issue that we see with the Tresca criterion. And instead of talking about principal stresses, the von Mises criterion just refers directly to invariants, where in the x-axis we're going to have the first invariant of the stress tensor, and in the y-axis we're going to have the square root of the second invariant of the deviatoric stress tensor. Okay, so, and here we're going to have von Mises is going to say that the maximum value or the state of stress is not limited. It can be whatever for the first invariant of the stress tensor, but the only limit is the second invariant of the deviatoric stress tensor, and let's say to a value equal to k. Okay, so let's see what that means in terms of von Mises. If you remember, the second invariant of the deviatoric stress tensor is defined as follows: is 1/6 of the summation of the differences between the principal stresses. And one more. And I can define what is going to be this value k for von Mises using the same kind of experiment that I did before, where in a typical pooling experiment, the maximum stress, the yield stress, is going to be sigma y, and at those conditions, I have, let's say that sigma 1 is going to reach the maximum value, and sigma 2 and sigma 3 are going to be equal to 0. So if I replace these two equalities into the equation on top, what I'm going to obtain is that J2 is going to be equal to 1/6 of sigma y squared, and this is going to be 0, and this is going to be sigma y squared. It's actually 2 sigma y squared, and that's going to be and let me now convert this to square root. Square root of J2 is going to be the square root of sigma y squared divided by 3, or in other terms, sigma y divided square root of 3. And this is actually our value k that we see over here. So let me take advantage of this plot. And in von Mises, this limit is going to be given by the yield stress measured in a pooling experiment without any stresses on the side, divided the square root of 3. Okay, notice that we have used the principal stresses, but we have gone through the second invariant of the deviatoric stress tensor, which is just one value. And as long as the square of J2 is equal or less than this value, then I'm going to be within the elastic region. All right, so we can also plot that in 3 dimensions, and it's going to look something like this. We're going to have here, similar as before, sigma 1 Roman, sigma 2 Roman, sigma 3 Roman. We're going to have our hydrostatic axis, where sigma 1 is equal to sigma 2 and is equal to sigma 3, and the von Mises criterion is going to tell me that I can move indefinitely along the direction of the stress invariant I1, and notice that the stress invariant I1 is actually telling you where you are in the distance from here to, let's say, from O to P. O to P is actually a function of the stress invariant. And you can do some geometry and find out that OP is going to be 1 over square root of 3 times first invariant divided by 3. So the stress invariant tells you where you are along this line, and the first stress invariant. And let me change this to blue. And the distance from the hydrostatic axis to any point is going to be given by J2. And let's go ahead now and draw a cross section of this surface with a plane perpendicular to the hydrostatic axis, and it's going to look like this. Well, let me do a little bit smaller. Okay, where if this is a point N on the yield surface, the distance Pn by geometry, you can find that is going to be equal to the square root of 2 times the square root of J2. This is just by geometry. And here now, since this von Mises criteria is smooth with respect to the angle that I go around the yield criterion, this is going to look like a cylinder in 3 dimensions. And this yield surface is going to be continuously derivable around the surface itself. We're going to see later on that that derivative is very important because it allows us to calculate the plastic strains. And in 3 dimensions, this is how the von Mises criterion is going to look. And further, let me tell you that from combining what I have over here, which is the limit of J2 for a typical material with a test doing a pulling just in one direction, I can combine this with the geometrical properties of the surface, and I can find out that the distance Pn, or the radius of that cylinder, is going to be equal to the this. Well, but actually what I want to do here is to take advantage of the of Pn. So no, I think I have everything. Let me check again. No, okay. What I wanted to do is to calculate Pn in terms of J2, and this is going to be square root of J2 is that. So this is sigma y, and let me just simplify it into 1 square root, 2/3 of the yield stress. And this is also what is known as the von Mises stress. So if anywhere on this circle you reach that value, then that means that you are at yield. All right, so let me see if I forget anything from here. I don't think so. So just let me give you one, tell you 2 more things. First one is that remember that, as we said at the beginning, these are yield criteria which are insensitive to mean effective stress, which means that you can move along the hydrostatic axis and you're not going to be ever in failure. Infinitely in compression, infinitely in tension, you're not going to be in failure as long as you're inside the yield surface. And this is not going to be true for rocks, and in general for all materials, but for the stress that we work with, for rocks, we cannot go infinitely in tension because we run into tensile failure. We cannot go infinitely in compression because we run into significant compaction strains. And the other thing that I wanted to share with you is this. And if you ever go to Paris, and most likely you're going to go and watch the Eiffel Tower, just pay attention that there are several names around the tower. And you will find von Mises, you will find Tresca, you will find Poisson, and you will find Navier, and many of the names of the people that have made or have established the basis of continuum mechanics.